This is Pope Leo XIV, the new head of the Catholic Church after the passing of Pope Francis. Unsurprisingly, with a new pope come new memes. But in the case of the new Pope Leo, you may be surprised that he has a bachelor's degree of mathematics, which means we're getting new Pope math memes. Some of these memes and jokes are mildly funny, like this one. We've got a bunch of formal logic hieroglyphics and then the Mr. Incredible comparison. But unfortunately, so many of these jokes are riffing on something that if it ever was funny, it certainly isn't now. And that's the fact that the abbreviation for the sine function is the same as the word sin. If you think this is funny, I'm happy for you, but I'm sorry, I'm just not capable of finding these sine jokes amusing. The reason I bring up the jokes, though, is that there is one joke about the Pope that I actually think is funny. Well, I call it a joke, but it's more of a comment, really. And this whole video is one big long lead up to this mildly amusing comment. It's a comment that plays on a much more interesting connection between faith and mathematics than the sine function does. We'll need some context first, though, so I'm going to tell you how to become Pope, how the new Pope became Pope, thus establishing the first ever math to Pope pipeline, and then we'll get into the math you need to know for the joke. I'll try to keep that math as accessible as possible, but for those of you who are into the math, which is probably most of you, there will be a proof of the infinitude of the prime numbers that you might not have seen before. This video has chapters, so you can skip around as you please. One quick aside before we begin the Pope talk in earnest. Some of you may be a little bit curious about the connection between mathematics and religiosity. It's not a stretch to imagine that, like scientists, mathematicians may be less likely to be religious, which might have made the Pope's math degree a little bit surprising. I don't have stats on this, but I will say, in the same way that the logic and axiomatic systems of mathematics might make someone less likely to be religious, the unbelievable beauty and order that emerges as a result of these axiomatic systems may just as well make a mathematician more likely to be religious. And you don't have to look hard to see math and religion intertwine. Just pick up a math book from a Christian school, for example, and you'll see comparisons between not adding fractions without common denominators and not yoking together in business with someone without a common savior. Reciprocal fractions and reciprocal relationships between you, your friends, and Jesus. And comparisons between evaluating functions and evaluating your life. Historically, of course, like the men of their time, many great mathematicians were quite religious. Leonard Euler and Bernard Riemann are two that come to mind I've been reading about recently, who both planned to become pastors, following in their father's footsteps, before their fathers approved of their decision to switch to mathematics. And good thing for the switch, because these were two geniuses who contributed immensely to mathematics. Well, enough of that, let's talk about how to become Pope. And just like we often do proofs, let's do it backwards. When the Pope dies or resigns, the next Pope is elected by the cardinals that are younger than 80. Currently, there are 251 cardinals, and the elected pope is almost always a cardinal. The most recent counterexample is Pope Urban VI, who was elected pope under dramatic circumstances in 1378. So you have to be a cardinal. But how do you be a cardinal? Well, cardinals are elected by the Pope, often from the bishops of the largest cities in their country. Then, to become a bishop, you have to be a successful priest in the area where a bishop position becomes available. Local bishops will nominate priests, a vote is carried out, and eventually the Pope gets the opportunity to veto or approve you as bishop. Then, to be ordained a priest, you must attend a seminary, which requires being a practicing Catholic and having a GED or high school diploma. So that's how to become Pope in a very brief front-to-back nutshell. The new Pope, Pope Leo XIV, was born Robert Francis Francis Prevost on September 14, 1955, in Chicago, Illinois. In 1977, he graduated from Villanova University with that beautiful thing we call a Bachelor's of Science degree in mathematics. In 1982, he obtained his Master of Divinity degree from Catholic Theological Union in Chicago. This is the degree that you obtain through going to a seminary. During his studies, he actually taught physics and math at St. Rita of Cassia High School. Then, on June 19th of 1982, Prevost was ordained a priest at a church just south of the Vatican in Rome. Skip forward to September 26th, 2015, he was named Bishop of Chiclayo, just about a year after Pope Francis had appointed him the titular Bishop of Sufar. Then, in the penultimate step, on September 30th, 2023, the term of art is that Pope Francis created him cardinal. Prevost served as cardinal until 2025, when, 17 days after the passing of Pope Francis, he was elected the new pope. He was considered somewhat of an unlikely candidate for becoming the next pope, one potential stumbling block being his American heritage. He's actually the first American pope, but on the other hand, he was also an ally of Pope Francis. Regardless, as of May 8th, 2025, Pope Leo XIV officially established the Math to Pope pipeline. Alright, with the Pope talk out of the way, we can start to get into some of the math. This is English mathematician G.H. Hardy. And he once said, "There is no permanent place for ugly mathematics." Mathematics, just like technology, can advance in its slickness and convenience over time. It's not at all unusual to see a proof of a theorem being a little bit rough and ugly at first, but over time, other people may improve on it, making it simpler or discovering entirely different proofs. Certainly, one of the beautiful things in mathematics that people love to prove stuff about is the primes. Prime numbers, you surely recall, are integers greater than 1 that are divisible only by 1 and themselves. There are numbers like 2, 3, 5, 7, and so on, numbers with no non-trivial factors. Over the years, many interesting questions have been asked related to the prime numbers. The most famous unsolved problem in all of mathematics is the Riemann hypothesis, which has an intimate connection to the primes. Easier to explain is an old problem like Goldbach's conjecture, another unsolved problem that states every even number greater than 2 can be written as the sum of 2 primes. We don't know if it's true or not, but certainly one of the very first questions asked about prime numbers was how many are there? This problem was resolved very quickly by Euclid around 300 BC. The answer is infinitely many. But to give you an example of ugly mathematics, necessary for the joke to make sense later, I want to show you a proof of the infinitude of primes other than Euclid's. Remember a moment ago I mentioned Goldbach's conjecture, which hasn't been solved. However, Goldbach himself did prove a theorem in a letter written to Leonhard Euler in the year 1730, and this theorem is going to be relevant to our discussion. However, to understand it, you've got to know what relative primes are. Relative primes are, I think, exactly what they sound like. Is 4 a prime number? No. Is 15 a prime number? Also no, but they are relative primes. We might also say they are coprime, and this is because they don't have any common factor greater than 1. Their greatest common factor, or greatest common divisor, is 1. The factors of 4 are 1, 2, and 4. 15 has 1, 3, 5, and 15. That's what relative primes are, numbers whose greatest common divisor is 1. They have no common factors other than 1. It's easy to think of numerous other examples, like 10 and 27, for example. The factors of 10 are 1, 2, 5, and 10. The factors of 27 are 1, 3, and 9. Also relevant to primes is a powerful theorem called the fundamental theorem of arithmetic. Most of you are likely familiar with this theorem theorem, but I don't wish to use its whole power in this discussion. We're only going to need this much weaker statement that's easy to accept. Every integer greater than 1 has at least one prime factor. One possibility is that the number is prime, like 2, in which case the number itself is a prime factor. The other possibility is that the number isn't prime, like 27, in which case by definition it would have some factor besides 1 and itself, and if that chosen factor isn't prime, we could look at its factors until eventually we arrive at a prime that's a factor of the original number. So no doubt every integer greater than 1 has at least one prime factor, and this means that if we imagine creating a list of primes, relatively prime numbers must account for additional primes. Here's what I mean. Consider the two numbers 4 and 5. Like we just said, any integer greater than 1 must have at least one prime factor, so these two numbers must each have at least one prime factor, but it's possible those prime factors are equal, except for the fact that we know 4 and 5 are relatively prime. That means 4 must have at least one prime factor, but 5 must also have a distinct prime factor. They can't share one, since they're relatively prime. I could throw another number in here, like 9, that's relatively prime to the previous two, and then this as well must account for at least one additional prime factor. 9 has to have at least one prime factor, and since it's relatively prime to these two numbers, it must be a new prime factor. In this case, from 4 we would get the prime factor 2, from 5 we would get the prime factor 5, and from 9 we would get the prime factor 3. We could go on like this, as long as I'm able to find another number that's relatively prime to all the others in our list, we would be guaranteed a new prime number. For example, the number 77 is relatively prime to all the numbers already in our list. Hence, having this number guarantees at least one additional prime factor, like 7. In this case, we could also pick out 11, but for sure we're guaranteed one new prime. This hopefully straightforward logic of a list of numbers that are all relatively prime, corresponding to a list of prime numbers, is the key that makes Goldbach's theorem a proof of the infinitude of prime numbers. His theorem concerned an interesting thing called Fermat numbers. These numbers are written as Fn and are numbers of the form 2 to the power of 2 to the power of n plus 1. They're named after Pierre de Fermat, famous for his last theorem. He was the first to study them, and he conjectured that all Fermat numbers are prime. F0, for example, is 2 to the power of 2 to the power of 0 plus 1. 2 to the 0 is 1, 2 to the 1 is 2, plus 1 is 3, and 3 is prime. Meanwhile, the next Fermat number, F1, is 5, which is also prime. F2 is 17, another prime. F3 is 257, also prime, and these numbers get pretty big pretty fast. Of course, the spoiler that Fermat was wrong is that these are not called Fermat primes, they're called Fermat numbers, because they are not all prime. That was actually shown by Leonhard Euler. But in that 1730 letter from Goldbach to Euler that I mentioned earlier, he proved something interesting that is true about the Fermat numbers. He proved this interesting recurrence that holds for n at least 1. This says that if we multiply all the Fermat numbers from the 0th up to the n-1th, the result is actually 2 less than that next Fermat number, Fn, which is the first one not included in the product. At a glance, we can see a couple examples of this looking at our small list from before. Look at this. If we take F0 and multiply by F1, we get 15. 2 less than the next Fermat number. Meanwhile, if we multiply all three of these, we get 15 times 17, which is 255, 2 less than the next Fermat number. And from this odd little equation, Goldbach showed that the Fermat numbers have no common factors greater than 1. That is, they're all relatively prime to each other. And this is because, looking at this equation, imagine adding 2 to both sides. That would show us that each Fermat number is 2 more than the product of all of the preceding Fermat numbers. Now, when we take a product of all the preceding Fermat numbers and add 2 to it, that only gives us room for one common factor between these two sides of the equation, which is the number 2. For example, if 3 is a factor of any of these Fermat numbers, it certainly can't be a factor of Fn, because Fn is only 2 more than a multiple of 3, because it's only 2 more than this whole product. So the only possible common factor between any two Fermat numbers would be 2, but we know from their definition that none of them are even. A power of 2 is always even, and when you add 1 to an even, you get an odd. So no Fermat numbers are even, hence they don't have any common factors. So if we prove this recurrence, the Fermat numbers qualify as a list of numbers that are all relatively prime to each other. The existence of a list like that would establish the infinitude of the primes. There's certainly infinitely many Fermat numbers, and every one of them would have to guarantee a new prime factor that hasn't appeared previously. And proving the result is straightforward using a method we call a proof by induction. First, we prove that the result is true in the initial possible case, which is when n is equal to 1. This is called the basis step, and often, as it does here, amounts to just writing out our result for n equals 1 and noting that it's true. If we're going from m equals 0 to 1 minus 1, well, the only Fermat number we're considering is f0, which we know is 3. And of course, 3 is 2 less than 5, and 5 happens to be the next Fermat number, f1. Hence, we've proven that at least in the first possible case, our result is true. The next part of an induction proof is what's called the induction step, in which we assume that our result is true for some number, usually called k. We already proved that our result is true for some number, so it's totally valid to assume that it's true for some number. We write what's called the induction hypothesis, which looks like this. This is just assuming our result is true for some positive integer k that's at least 1. From this assumption, we'll show that our result must also be true in the next case, k plus 1. Thus, we will have shown that not only is our result true for the first number, but if it's true for some number, it must be true for the next. Thus, that shows that it's true for all numbers, by what's called the principle of mathematical induction. Now, to show the recurrence is true for k plus 1, we would look at the product of the first k Fermat numbers. Of course, it's our objective to show that this product is 2 less than the k plus 1th Fermat number. Of course, the last number in this product is fk, the kth Fermat number. So let's just factor that out of the product and write it on the outside. There's fk, and what remains is the product of the first k minus 1 Fermat numbers, which is what our induction hypothesis is about. This product of the first k minus 1 Fermat numbers, we know from the induction hypothesis, is fk minus 2. So we rewrite this as fk, that's still on the outside, and then this product we know from the hypothesis is fk minus 2. Then we can replace both of these fk's with what they are equal to by definition of Fermat numbers. Fk is 2 to the power of 2 to the power of k plus 1. And fk minus 2 is the same thing, but we have to take 2 away from that plus 1, so then it's actually minus 1. Hopefully you're familiar enough with your factorizations to know that this is how we factor a difference of squares. So in fact, if we multiply these things together, we would get the square of this term minus the square of this term. If we square 2 to the 2 to the k, we get 2 to the 2 to the k plus 1. And then minus the square of 1, which is of course minus 1. Now notice this is the power of 2 that would appear in the k plus 1th Fermat number, but that Fermat number would also have a plus 1 on the end. Instead of a plus 1, this has a minus 1. That's a change in 2. It's a difference of 2. It's minus 2. So this is actually the same as the k plus 1th Fermat number, but then minus 2 to change the plus 1 in the definition to to the -1 that we actually have. Together, the basis step and induction step prove this recurrence, which establishes that Fermat numbers have no common factors, and like we said, that implies there are infinitely many primes. So we have just done a heck of a messy proof that there are infinitely many primes. When a student is first told about the infinitude of primes and the proof of that result, this is never the proof they're shown. They're shown the proof that is attributed to Euclid. And I think you'll agree that Euclid's proof is a lot more quick and punchy. In Euclid's proof, we consider a finite list of primes, P1 through PR. Then consider a new number, formed by multiplying all of those primes together and adding 1. We'll call that number big N, so it's equal to P1 multiplied by P2, and so on, all the way up to a last multiplication by PR, and then 1 is added to this number. We then ask, does N have any of these primes in the list as a factor? The answer, of course, is no, because N is equal to a multiple of all of them, plus 1. For example, N can't be divisible by P2 because N is 1 more than a multiple of P2. That doesn't leave enough room for another P2 to fit in and make N a multiple of that number. Just like 11 obviously isn't a multiple of 5 because it's 1 more than a multiple of 5. There's not enough room to fit another 5 in there. Since N isn't divisible by any of the primes in this finite list, N itself must be prime, or have some other prime not in the list, as a factor. This means that no finite list of primes can be complete. No finite list can contain all of the primes. Hence, there are infinitely many. For brevity, I haven't written out every single detail of the proof here, but I think most would agree that this is the superior proof. Furthermore, it's probably the proof in the book. What is this so-called book? It's basically where all of the beautiful mathematics lives. As humans with limited knowledge, sometimes we have to deal with the ugly math. But prolific Hungarian mathematician Paul Erdos loved to talk about the idea of God having a book. The book of all the perfect proofs, the most lovely and beautiful proofs of all of our favorite theorems. In fact, there's an actual book called Proofs from the Book, containing some of the proofs that we think might be in that big book. And it actually includes the Goldbach's theorem proof for the infinitude of primes, though I think none will argue that Euclid's is the most timeless and elegant. Showing some support of the pursuit of beautiful mathematics, Paul Erdos is quoted as saying, "You need not believe in God, but as a mathematician, you should believe in the book." Now, the joke, which will no doubt disappoint after all this time. Now that the Pope has a math degree, maybe we'll finally get a look at what's inside that ding-dang book. I'm unstable, revealing art to keep the cable cut and untuck the table. If Texas Instruments don't reply, well, I think this time it might be fatal. Wish to sell my own fake, cause I'm jaded. Hate the odds that I calculated. Press and pull and pray and push it all the way through the whole blue planet faded.